So, this is one algorithm where you have shuffled input samples. I can also do the same operation by doing shuffling on the output samples. Keep the input sample same, the same, but you shuffle them with this algorithm. Then changes, but that matrix, modified matrix, you can also be broken down into similar manner. And if you remember, this is the examination problem in 102, right? If you shuffle the, right? Good. Some of you remember. So, this is the shuffling in the frequency domain. Okay. This, remember all the, I am just making some observations, do not take as a part of your examination or something, because you must understand this thing clearly. I assumed n is of the form 2 to the power of p. So, number chosen of the samples is equal to a power of 2. So, you have now 512 samples or 1024 samples or 2048 samples, and the number goes, difference goes much larger. So, what do you do if the samples are not this number? Doesn't fit into 2 to the power of p. Only alternate that for you to put zeros in it. So, take an artificial signal with the additional number or it is required to be equal to 0, and the signal you will get will be with having some zeros at the end of it, and don't bother about those zeros. So, this is called radix to f of t. What we are doing, because the power is of 2 to the power of something. In theory, you can also take any radix some q to the power of p, some other p. Q can be any prime number. So, you can talk in terms of similar algorithm for different values of radix other than 2, as long as the radix is a prime number. But the algorithm because it is a binary computer after all. So, all these are theoretical interest, not of any meaningful interest, because everything has to be 2 in a binary computer. So, all this is for theoretical interest, not for any practical interest. So, all the time the most common thing is 2 because of the binary computer that we have here. And lot of work has been done on this radix, prime radix algorithms, but meaningless in terms of practice. What else do I have to say on this Fourier transform, DFT? I think I have. Now, let me say something else. X of m right. Let me play a trick. Mn is equal to m minus 1 square minus m square minus n square. Yes or no? This is m square plus n square minus 2mn divided by 2. And there is a 2 here. Okay. So, 2mn can be written down as equal to minus also goes. Okay. Let me rewrite this as now leave this for the time being and just look at this. The signal is x of n number of samples, capital N number of samples for x of n, whose Fourier transform is what you are looking for. So, if I take that samples multiply by this function, I get a new series g of n. If g of n is to be operated by this with a and look minus n, it looks like our correlation, I mean convolution. So, this operation is nothing but g of n convolved with e to the power of j pi by n. You agree or not? Because this is convolution. So, if you do this convolution, you get this summation. Doing summation is convolution, the summation is taken care of, you get this function. This function has to multiply by e to the power of minus j pi n by m square. So, you multiply by e to the power. That will give you Fourier transform, DFT. Very simple, but very interesting.